Alright guys, so let's start. I'm going to do questions 1, 2, 3 in this video, and this is for the B.1 angular momentum practice set. So the diagram below pertains to questions 1 and 2. A cylindrical object rolls down a ramp. The moment of inertia is 1/2 mr squared. Derive an expression for the linear acceleration. Friction coefficient is unknown. So the only force that gives rise to a torque acting on this object is the friction force. And we don't know the friction coefficient. So in this case, if the friction coefficient is unknown, I need to analyze the linear forces acting on it. So I know that even though the object is rolling, that it will also be translating linearly. So there will be a F net, a linear force acting on the object, and there is also a force down the ramp, F down. There is the force of friction, and there is the F net. So I can make a net force equation for the linear direction. So F net equals, the force down goes in the same direction, so that's positive, minus the force of friction. I need to solve for this force of friction. It will be unknown because now I have my friction coefficient is unknown, and in the previous problems I gave you a friction coefficient. So the net force, the linear force on an object, is always the object's mass times its linear acceleration, equals the force down the ramp. This is m times g times sine theta minus force of friction. So the force of friction then, if I add it to both sides and subtract ma from both sides, equals mg sine theta minus ma. Okay, so I have this value for the force of friction, and I need to relate it to torque. So remember, torque has two expressions. Always when we're dealing with rolling motion without slipping, we're going to use these. One is I times alpha, which also becomes I times the linear acceleration over the radius or the distance from the axis of rotation of the rolling object, and torque is equal to the force which causes rotation. In this case it's friction, so the force of friction times r times sine theta. In this case the angle between the r, my moment arm, and the force of friction is 90 degrees. So now I have an expression for the force of friction, which I'm going to put into here, and I'm going to continue this problem below. Torque is equal to mg sine theta minus ma times r, and torque also equals I times a over r, and I'm going to plug in 1/2 mr squared for my I, so torque also equals 1/2 mr squared times linear acceleration over r. And you'll see now that by solving for the force of friction, plugging in for my torque equation, using my second torque equation, I can set these two equal to each other, and I'll only have my one unknown, the linear acceleration. So I'll go ahead and do that. I have mg, open parentheses, sine theta, which is the angle of incline, minus the linear acceleration times r. I set that equal to 1/2. The mass, sorry I used capital M, it's the same, it's all the same mass, lowercase m times r squared times the linear acceleration over r. Now I'm going to divide by r on both sides, and you'll see that when I do that, all of the r's will cancel. So this expression becomes mg sine theta minus ma equals 1/2 m times a. I then add my ma terms to both sides. mg sine theta equals 1/2 ma plus 2 over 2 ma. Notice that I've just changed ma to 2 over 2 ma. So see how that simplifies? Then I can factor, let me combine these two. So I have mg sine theta equals 3/2 m times a, and now you can solve for a. The acceleration, my m's cancel, the acceleration equals 2/3 g sine theta. And that's the answer. So this is what you do if the friction coefficient isn't given. Only if the friction coefficient is not given would you really need to analyze the linear forces. Still, the only force that gives rise to rolling motion without slipping is the friction force. Excuse me, this should have been totally parallel to the slope, but you get the idea. All right, if theta equals 25 degrees, find the time it takes to travel down, to travel 0.95 meters. The cylinder starts from rest. So you have your angle, you know your acceleration. This is now just a kinematics. Use kinematics to solve for t. A you'll solve. A equals 2/3 times g times sine of 25 degrees. Initial velocity is 0. Your displacement is 0.95 meters, and you are looking for t. So find an equation that you can use to solve for this. For number 3, a skater is spinning at 32 rads per second. This is her initial angular velocity with her arms and legs extended outwards as shown. So this is her before. In this position, her moment of inertia with respect to the vertical axis about which she is spinning is 245.6 kilogram meters squared. This is her initial moment of inertia. She pulls her arms and legs in close to her body, changing her moment of inertia to 217.5 kilogram meters squared. What is her new angular velocity? So this is her I final. So in this equation, we know, in this scenario, we're taking advantage of the fact that angular momentum is conserved. Angular momentum is always conserved. And angular momentum is similar to linear momentum, P. If P is m times v, then angular momentum is the moment of inertia times omega. So delta L is 0. That means L final minus L initial is 0. That means the final angular momentum equals the initial angular momentum, and then we can just plug in for her values and solve. I initial times omega initial equals I final times omega final. Plug in for the values. We have 245.6 kilogram meter squared times 32 rads per second equals this final 217.5 kilogram meter squared times her times her final angular velocity, omega final. This is our unknown, and you can solve for it. Okay, up next I'll be solving the next page of these practice problems. Thanks for watching.